guys all know Professor Chu is out of town, so today I'll be teaching this class. And I don't think the TA is assigned yet, but you can always email Professor Chu if you have any problems or office hours. Yeah, so today I'll be doing quite a bit of derivation, but just don't be scared by these math, because I don't think this class is intended for math class. The important thing is that what you can see from the derivation, and what kind of physics you can see from the expressions. And I guess it's always impossible to memorize all these stuff, but what can stay in your mind is how we get there, and I think that's more important. It's just my personal experience. So today I'll be talking about reciprocity theorem, Green's function, Green's principle, and uniqueness theorem. All right. So let's start with the reciprocity theorem says that if you have a source here, and if you have another source here, then the field generated by these sources at this point, it's if you have the same the field generated by the source here is the same as if you switch the location between the source and the observation point. And the more general form is that if you change a different source, but the reaction between the field here and the source would stay the same as the reaction between the field here and the source here. So in electromagnetics, we use E field and the current. And in the circuit, you may use the current and the voltage. So now before we start deriving the theorem, we first define a reaction between the field and the current. So we first define this reaction of two vectors as an inner product between these two products. So for those who have taken quantum mechanics or waveguide theory, you may notice that here we are not using a complex conjugate for A here, not like the Dirac notation. The reason is that the reaction between the two vectors is not physical quantity, but it doesn't carry a physical meaning like power or probability, but it's just the reaction between these fields for us to measure this reciprocity. So now that we have defined this inner product, we can start with the vector wave equations that you guys learned last time. So make sure I get everything right. So simply plugging the second Maxwell equation into the first Maxwell equation. But here I keep all these as tensors, meaning that I account for all the anisotropic medium, and also I keep these within the derivative. So meaning I'm accounting for the inhomogeneous medium. So the second equation will just changing the index from 2 to 1. So now we want to see the reaction between the current and the E field. So what we do is just to dot this equation with the E field from generated by the source 2, and then we do the inner product. So now we can see if we move these two terms over here, we'll have I omega, the reaction between E1 and J1, minus the reaction between E1 and rho of sorry, I should use E2. Then I can have the second equation. Just change the indexes. So our goal is to prove these two the same. So if we look at the right hand side of this equation, we can see these two terms look very similar, right? So how do you make these two the same? So we know that this inner product is like a row vector times column vector. So this inner product is a scalar. You can see this. So the scalar is transposes itself. So we can see that this E2 inner product with epsilon E1 should be the same as E1 inner product with transpose of epsilon E2, right? Because this is a scalar. So comparing this to this, we can see that as long as epsilon transpose equals to itself, then these two are the same, right? So this keep in mind this condition, this epsilon transpose being itself. So now we can get rid of these two terms if we have this condition. So let's look at this term here. So now we have this inner product between E2 and cross mu inverse. So if you look at these two terms, if we can somehow put this derivative to here, or put this derivative to here, then these two terms looks very similar, right? We can put this this curl to this E2, then it becomes curl of E2 mu inverse and curl of E1, and this becomes curl of E1 mu inverse curl of E2. So what we need to do is just move this to here, and the way we do it is by chain rule, and then we'll be using this a lot in this class. So now this becomes an integral of E2 curl So we have to use a vector identity here. It's the divergence of two vectors crossing each other will become and the reason we want to make this divergence here is that we can use a Gauss theorem. And then this is how we usually get rid of terms using the Gauss theorem here. So here, it just become, moving that term over here, it will just become divergence of E2 cross. So I have, if E2 is A, and this is B, so I have divergence of E2 crossing this one. So I have mu inverse down plus E1. And then I have moving this term over here, it will have this so is everyone okay so far? Okay, now we have this looks very symmetric here, so we can just try to get rid of this term using the Gauss theorem, and this will become a surface integral. But the trick here is how to get rid of this term. So here we need to make an assumption here. So the assumption here is we are considering a very large volume, so that we can get rid of the few terms at the boundary. So the assumption is that the V is approaching infinity. And as the V approaches infinity, we can see that the field generated by the source approaches the plane wave. So using the plane wave assumption, then this del function will just become IK, where K is the plane wave wave vector. So now this term, you can see that this is another. Also, another assumption is that we have to assume this to be homogeneous as the V goes to infinity. So this we will have A cross B cross C, and this will give you B so we have E2 cross this becomes IK, right? So this term will just approach A cross B cross C becomes K, and E2 dot with E1 minus E2 dot with IK. E1. And this will go away when it becomes a plane wave, so the wave becomes all transverse. So this will go away. And this term we can see it's symmetric, right? Its transpose is the same as itself. So the whole idea is to prove the term to be symmetric. So now, using this assumption, this first term becomes symmetric. And this term, when mu is the same as its transpose, meaning mu is symmetric, then this term will also become symmetric. So that, meaning that this curl of E2, mu, curl of E1, inner product will become the same as itself. So now we have proved these two terms to be the same. Given the condition of mu transpose equals to itself, symmetric. So now what's remaining is this term. Is that everybody okay with here? So let's look at this term. We have the inner product of ER. So again, we use the same trick as here. We have a vector dot with a curl of something. Except that now I replace this by mu inverse M1. And in the end, I will get to two terms, right? One is the this divergence term, and the other is this term. So it will become a surface integral of E2 cross mu inverse M1 plus the volume integral curl of E2 dot mu inverse M1. So now to throw away this term, we have to assume that the source is finite. So we can always make the volume integral very large, so that outside of certain volume, the source will become 0. So we can choose such a surface to make this term 0. All right. So what we have left here is just this term. Okay. So what does the curl of E2 mean here? Means the magnetic field, right? So now we can have change this to the magnetic field generated by source 2. So it's just inner product of the magnetic field dotted with the magnetic current of source 1. Okay, so this term becomes inner product between H2 and M1. And this term will become an inner product of H1 and M2. And these two terms will just cancel out. They will be the same given this condition. So eventually we'll arrive at the reciprocity theorem as Alright, but keep in mind that I have thrown away a term here. This based on this assumption that the volume is infinity. But if the volume is not infinity, we can, if we look at this term, what does this mean? Magnetic field, right? This is a magnetic field generated by source 1. And this is the E field generated by source 2. So this simply becomes an surface integral of E2 cross H1 on this finite surface if this surface, if the volume is not big enough. And the other term coming from it here will give me another term of E1 and H2. So, so this is actually based on assumption that the volume is infinity. But if the volume is finite, we should add two more terms here, which are the surface integral of E1 cross H2 and E2 cross H1. And this is called, when you add these two terms, it's called Lorentz reciprocity. All right. So let's look at these two conditions. So these are the conditions for the medium to be reciprocal. If you remember from last class, I think, what's the condition for epsilon and mu so that the medium is lossless? Emission, right? So this is a condition for emission, for a lossless medium. So the question is, can a lossy medium be reciprocal?
Real. I mean, all the matrix elements are real. So lossless medium.
Lossy medium. Can lossy medium be reciprocal? Can. Right. Because as long as you satisfy the transpose being the symmetric property, then even though it's non-Hermitian, it can still be reciprocal. So the simple case is that say I have isotropic medium, and I have this epsilon become a scalar instead of a tensor, but I can still have the imaginary part of the epsilon, right? Then we can see this is it's not Hermitian. It's a transpose. It's conjugate transpose is not itself, but it's transposes itself. So this medium is lossy, but it's still reciprocal. So that's one thing to note. So so what we can usually see that the lossy medium can still be reciprocal, but some typical non-reciprocal medium usually involves ferrite material and something that probably that can be changed by magnetic field. So when you see the epsilon or mu tensor, it has off-diagonal elements, which are imaginary. That's typically what we've seen for the non-reciprocal material. All right. So, questions so far? All right. If not, I'll start talking about Green's function. So, when you first learn Green's function, it may seem a little bit scary, but what I want to say is that to electrical engineers, Green's function are not just some mathematical tool, but it actually carries physical meanings to us. If we can see what it means, then I think the picture will be much clearer. So for me, I always like to understand this in terms of signals and systems, or like what we learned in as an undergrad. So say I have an input of I, which has a response of some kind, or if you want to do it time domain, that's my input. If I feed this input into a system, then what would the output be? So we know that the system can be characterized by a system function, we usually call H omega, right? This system response. And the output will just be the product of the system response and the input, right? So if we do it in time domain, it will be simply a convolution, because the Fourier transform of a product will be the convolution of two individual Fourier transforms. So it will become this. So, but how do we know this system function? Right. We send an impulse here, and then the output will just become the system function. And why is that? Because if we send a delta input here, what's the Fourier transform of a delta function? It's a flat line, right? And this will be 1. The output will be exactly my system function. So that's why this H is also called impulse response. So the idea of Green's function is also very similar. So now I have a source, J, at a certain location. And I want to know the field generated by this source. What I need to know is just the some system function that can represent the radiation environment where this source is, right? And this is actually the Green's function we are looking for. So we can guess that the output, the E field generated by the source would just be similar to here, right? Here is a convolution, and here we can expect that this is also a convolution of the input and the system function, right? So we can guess that this will be some kind of convolution here. Right, except that we don't know what's the detail here, but we can expect to be like this. Another thing to note is that this system has to be linear, so that the source can be linear superposition of its representation at each delta point, so that I can sum up the contribution at each point of the source and use the response of that delta source and something up to get the output of the field. Right? So now let's start with the simplest form of Green's function, which is the scalar Green's function in free space. So now say I have this wave equation, and I want to know the solution to this wave equation due to some source S. And then I know that the Green's function is the impulse response in this environment. Okay, and then now we can see that, so to simplify the derivation, I can shift the whole system. Right now the source is at R prime, right? The delta source is at R prime. I can shift the whole system from R prime to the origin, and the problem still stay the same. It's called, I think in math it's called stationarity. So I can shift the whole system to the origin without loss of generality. So now I can set this R prime to 0. But later on I can put it back, because what it matters is the relative distance between the R and R prime. So later on I can just put this R prime back. So now we have a much simpler form of this Green's function. And then we can see that for R not equal to 0, this wave equation will, the right hand side will just disappear, right? And because it is in free space, I can use the spherical symmetry, and then we do this problem in spherical coordinates. In this way, then the partial phi and the partial theta in the Laplacian will all both go to 0. And then the Laplacian in spherical coordinates will just become this. You can always look up in the table. But it's always good to check the unit. It's this should be 1 over length squared, right? Here, square, square. Okay, it's good. But now I have to do something here. So we, what I want to do is I want to put these two derivatives together, become a second derivative. So what we can do is again use the chain rule, and then it will become 2R. So I want to make it to something. Of course, this I already know the solution. So I want to make it into something like this. like the units are correct. And then this you know from when you solve the spherical wave equation, you know that in Cartesian coordinate you can decouple all three directions. In cylindrical coordinate you can only decouple the z component, but in spherical you can decouple none of the components. But if you multiply the wave function by an r, then actually you are able to separate the radial part and the other theta and phi part, which they solve they call the spherical harmonics. They solve that differential equation. So now I can I just need to show that this is actually the same as this one. So I can always add a function here. It's easier to do. So. And this will give me another, give me a second derivative of f plus another first derivative than this, and 1 over r. And then adding another term from here, it will give me 2 times of 1 over r partial r f, which is exactly the same as this one. So the whole purpose is to replace this this term by double derivative here. So now this becomes the wave equation just becomes 1 over r partial r squared rg plus k squared g equal to 0. And then I move the r to